Hey there! So you're getting started with FEA, huh? Well, today, we are going to solve one of the most common puzzles you're going to face, RBE2 versus RBE3. In just a few minutes, you'll know exactly which one to choose every single time. Let's jump right in.
So tell me if this sounds familiar. You create one of these spider connections, you hit the solve button, and all of a sudden your nice, flexible part is acting like it's made out of a block of concrete? Yeah, don't worry, we have all been there. It almost always just means you pick the wrong tool for the job.
So first up, let's talk about the RBE2. The best way to picture this is as the bossy rigid plate. You've got one central node, okay? That's the boss. And when that boss moves or rotates, all the other outer nodes, they have to follow its every single command perfectly. It's like they're all welded to an infinitely stiff plate. No wiggling, no independent movement. They move as one single rigid thing.
And then you have the RBE3, which is, well, it's the complete opposite. I like to call this one the democracy, or the averaging team. The roles are totally flipped. Here, the outer nodes are the ones in charge, and that single central node, its movement is just a weighted average of what all the other nodes are doing. It's listening to the group instead of bossing them around. See the difference?
Okay, so this table right here, this is the whole game. Look at that very first row, stiffness added. For an RBE2, it's infinite. It literally pours digital concrete into your model. But the RBE3, it adds zero stiffness, zilch. It's designed specifically not to stiffen your part, and that is a huge deal. So you use RBE2 for truly rigid connections, and you use RBE3 when you just want to spread out loads and mass.
And this picture just shows it all perfectly. Look on the left. With the RBE2, that hole is forced to stay a perfect circle because of all that artificial stiffness we were just talking about. But on the right, the RBE3 lets the hole deform naturally. It squishes, it becomes an oval, like it would in the real world. Which one of those looks more like real physics to you?
So, how do you choose? It all boils down to one simple question. This flowchart right here is your new best friend. I'm serious. Ask yourself this one thing every time and you will never get it wrong.
So, question number 1. Do you actually need physical rigidity? Are you modeling something like a big, chunky, welded bolt connection, or a super stiff mounting plate that really isn't going to deform? If the answer is yes, then hey, RBE2 is your tool. Simple as that.
But what if what you really need to do is just spread a force or some mass over an area, and you absolutely positively do not want to add any fake stiffness to your model? Well, then you need an RBE3. This is usually the more common scenario, and frankly, it's often the safer choice.
Let's look at a perfect example. Here we're modeling a bolt holding two plates together. It's a really good engineering assumption to say that the bolt and the area right under the washer are very, very stiff. So using an RBE2 to connect the center of the bolt to the nodes around the hole, that's a perfect use case.
Okay, but what if you've got a force acting from a distance, and you don't want to just jam it onto a single node and create a big stress hotspot? You use an RBE3. You apply the force to that central node, and the RBE3 cleverly smears that load across all the surface nodes without locking them up. So much more realistic, right?
Here's another great one for RBE2. Just picture a heavy engine block bolted to a frame. That mounting bracket itself is super chunky and rigid compared to the thin frame, right? So modeling that bracket's attachment point with an RBE2 is a really smart way to capture that rigid behavior without having to mesh the whole complicated bracket.
And for an RBE3, think about a soft rubber pad pushing on a surface, or maybe the distributed load from a bearing. You want to apply that pressure, but you don't want to make the surface underneath it artificially stiff. RBE3 is perfect for this. It lets the structure flex and bend exactly like it's supposed to.
Now, quick heads up for those of you who also use Abacus. Don't you worry, everything you just learned translates directly. What NASTRAN calls an RBE2, Abacus calls a kinematic coupling. And what NASTRAN calls an RBE3, well, that's a distributing coupling in Abacus. It's the exact same behavior, just a different name. Got it? And hey, making them in Abacus is a piece of cake. You just go to the Interaction module. From there, you click Create Constraint, pick Coupling as the type, and then you'll see our two friends, Kinematic for that rigid RBE2 behavior, and Distributing for our flexible RBE3. It is really that simple.
Okay, now, lean in for this part. This is super important. This is the Senior Engineer's How Not to Break Your Model checklist. I'm about to walk you through 6 critical warnings that will save you days of debugging and so many headaches. Trust me on this.
Warning number 1, and it's a big one. A node can only have one boss. If you try to make a single node dependent in 2 different R elements, the solver just gets totally confused. It doesn't know who to listen to, and it will almost always just give up and throw a fatal error.
Second warning, never apply a fixed boundary condition, an SBC, directly to a dependent node. Just think about it for a second. That node is already being told how to move by its R element. If you then also tell it, by the way, don't move at all, you're giving it 2 conflicting commands. It'll overconstrain your model, and your results will be total garbage.
Warning number 3. These elements, they're really only designed for small movements. They assume things aren't bending or twisting all that much. So if you've got a model with really large rotations or big deformations, these simple little constraints are just going to give you the wrong answers. For those big nonlinear jobs, you need a different tool.
Here's a piece of wisdom that will save you days of your life. Before you stick a complicated spider connection into your massive multi-million node assembly, just build a tiny little test model, just a few elements. Make sure it behaves exactly how you think it should. It takes 5 minutes and can save you hours of pulling your hair out.
You have to be intentional with your connections. When you create the element, the software is going to ask you which degrees of freedom you want to connect. Think about it carefully. Do you just want to link the up-down, left-right movements? Or do you also need to link the rotations? If you constrain rotations when you shouldn't, your model can get bizarrely stiff in bending. So be deliberate.
And finally, the last one. If you are ever unsure which one to use, especially when what you really care about are accurate stress results, just start with an RBE3. Because it doesn't add any of that fake stiffness, it's almost always the safer bet for preserving the real physics of your model.
So if we wrap all of this up into one golden rule of thumb, it's this. Start with an RBE3 unless you can absolutely prove to yourself that you need rigidity. And no matter which one you choose, always test it on a small model first.
And that's it. You're all set. Go ahead and save this explainer because your brand new RBE2 versus RBE3 cheat sheet is officially ready to go. Happy modeling!